Good afternoon, class. We are going to start chapter 6, which is work and energy. And before you start working on work and energy chapter, start thinking about how many forms of energy that you can identify around you. Since energy plays an essential role both in everybody's life and also in everyday events, and also above all in the scientific phenomena. So I'm sure you can name many forms of energy from that, for example, by provided by food, to the energy that we use to run our cars, to the sunlight that warms us on the beach. We can also cite examples of what people call energy that may not be scientific, such as someone having an energetic personality is not the same as having energy. So those are literal meanings of that. Not only does energy have many interesting forms, it is involved in almost all phenomena and is one of the most important concepts of physics, because energy involves conversion from one form to another, and energy can never be created on its own, or energy can not be annihilated, like you cannot kill energy. So energy can only transport from one form to another. That's why we have this famous quote, energy can neither be created nor destroyed, it can only be transformed. So in this chapter, which is, I think it's very interesting chapter, we will work on work done by constant force. So work can only be done if you have energy. So work done and energy are used equally. So you'll see many examples of that work done and energy are basically the same, and energy is the capacity of the body to do the work. So then we'll also in this chapter discuss different forms of energy. Mind you, this chapter only deals with mechanical energy, so we are not going to be talking about chemical, nuclear, solar, or any other form of energy, since physics 1 is only focused on mechanics. So we will only talk about kinetic energy, potential energy, gravitational potential energy, and so on. So not all the forms of energy. Then we'll also talk about conservative and non-conservative forces, what they mean, and how to convert mechanical energy from one form to another, and all the problems that are can be solved using the conversion mechanism. And lastly, we will work on power. These are the only portions that are covered from this chapter. The portions that we don't discuss in here, you can already see there are, if there is 6.1, then you're immediately getting 6.3. That means I have deleted 6.2. 6.2 I think is variable force, so I have deleted that. So don't do that part. So let's start discussing what work means. So what according to you is the work? The scientific definition and the literal definition of work is different. The scientific definition of work differs in many ways from its everyday meaning. Like certain things we think of as hard work, such as writing an exam, or carrying a heavy load on the level ground and not going anywhere, is not work done. Doing exam is not work done, sorry. As scientists do not define work like that. For a scientific definition of work to hold good, there needs to be a relationship to energy. Whenever work is done, some energy is transferred. So that is the actual scientific analysis or scientific definition of the work. For work in scientific sense to be done, in order to achieve that goal, to do the work, we need to apply force. So definitely my work done must have force in it. So it's common sense. If I apply force, I may be displacing an object. I apply the force and the object will move, or it may not move. So if it moves, it has covered a displacement. So if it covered some distance, then it's possible to say that work was done because you were successful in displacing an object. So basic definition of work is then therefore given by work is equivalent to force times distance into cosine theta. Now you must be wondering, where did this cosine theta come from? This is a scenario of the force applied at an angle. There are some examples where you apply the force directly in the horizontal direction and the object moves, right? So this same object is displaced through a certain distance d. And the angle theta is the angle between force and distance. So if force is applied in this direction and displacement is also in this direction, what is the angle between the two? They are parallel. So theta must be 0. When cosine of 0 degree is 1, so then work done will be simply equivalent to F into D, because your theta is 0. Cosine 0 is 1, right? But when, in this case, in this scenario, when force is applied at an angle, it forms two components. One component is in the y direction and one component is in the x direction. This is the x direction component, this is the y direction component. Actually, I should make the vector smaller. So this is f of y. But the object is not moving in the y direction. So the work is not done in y direction. The object is getting displaced in the x direction. The component that is responsible for making it move in the x direction is fx. And you already know this. We have been doing the resolution of vectors. Fx is nothing but f of cosine of theta. And that is why we are using this fd cosine theta. So if work done is fx component, which is the horizontal component, into the displacement, then this becomes f cosine of theta multiplied by d, or we can simply write it as fd cosine of theta. So you must remember, theta is always the angle between f and d. All right. So that is the actual definition of work done. Now that we know that work done is force and distance and cosine of theta, it's time to find out what are the units of work. We know that force is measured in newtons and distance in meters. And the distance is measured in meters. We get the new unit, which was named in honor of the scientist Joule, who gave us the mechanical equivalent of heat, and he was the first one to work on finding out the equivalent of heat energy. So that's why we honor him, and we have the unit of the work done as joules. Joule is simply 1 Newton into meter. Angles have no units. Degree is not counted as an SI unit. So there's an interesting thing to remember about this. Energy or work both have the units of joule. Energy is basically stored form of work, and work is energy is the ability of body to do the work. So if you have energy only, then you'll be able to do the work. So the energy converts to work. So that's why the units of both of them are joules. Any time you define energy, you will simply use the unit joules, which is the SI unit, and all other quantities which are inside it should also be in SI units. So there are different scenarios of work being done. If this person who's holding this bag for hours and hours together and does not displace, then he has done no work because he has not displaced. But if he walks and moves and covers a certain distance, then we can think, okay, he did cover, there was some force acting, and he was applying some force in the upward or downward direction, but still he didn't do any work because he did not apply force in this direction, even though he was moving. As long as this person does not lift or lower the bag of groceries, he's doing no work on it. The force he exerts has no component in the direction of motion. So he's simply walking and carrying the groceries. He has done no work. Even if you will come home sweating that you had this big bag in your hands, but you practically haven't done any work if you have not applied any force on the bag. So remember, in scientific world, work has a very different meaning than the actual work that you think about. Here are some of the other examples. For example, this is work because the person who's mowing the lawn has applied force at an angle, and the x component of this force, which is in this direction, and the y component is not important at all, does no work. So helps us mow the lawn because the lawnmower is getting displaced. Hence, work done is ft cosine theta. Similarly, look at this example. When the person is holding the briefcase and not, the force is acting in the upward direction and not displacing, he has simply done no work. All right. And in case number C, do you think he has done any work? No. The force, the angle between the force and the displacement is 90 degrees. So work done is equivalent to force into distance into cosine of 90 degrees. Cosine 90 degrees is 0 because the force has not been applied in such a way that it causes the box to move. So the work is done on the briefcase by carrying it upstairs. If I use the same example and carry the briefcase up, then work is done. But in part C, the person moving the briefcase horizontally has done no work because there's an angle of 90 degrees between the two. But over here, if I can, the force is applied in this direction at an angle. So remember, theta is always, in the work formula, theta is always the work between, angle between d, the displacement, and force. So definitely some work is being done. F cosine theta component of this work will help get us the work. In the last example, when the briefcase is lowered, so we have this electrical generator, the box is going down, but the force that the electrical generator is imparting is in the upward direction. Hence, the angle between the force and the displacement is not 0 and is also not 90 degrees, it is 180 degrees. So the work done will be negative because work done is equivalent to force times distance cosine of 180 degrees. Cosine 180 degrees is equal to -1. Therefore, work done is minus F into D. So that's what the explanation for this is. Here, the work done on the briefcase by the generator is negative. They are acting in the opposite. The force is in the upward direction, the displacement is in the downward direction, hence the negative work being done. All right. So we have already discussed this. Work and energy will have same units. Newton meters is 1 joule. Remember that. And 1 joule is not large amount of energy. It would lift a small 100-gram apple a distance of about 1 meter. So don't think 1 joule is a large amount of energy. So how will we solve the problems? Now, to solve a problem, for example, I ask you, what was the work done in moving a box of mass 10 kgs from its position x not equivalent to 0 to a new position x of 3 meters if the force was applied was 20 newtons? Can you find the work done? Yes, I can, because work done is force into distance into cosine of theta. where force is 20 newtons, distance is 3 meters. Cosine of theta, you might have guessed, theta is 0 degrees because the angle between force and displacement vector theta is 0. So that becomes 1, cosine 0 becomes 1. So I get 60 Newton meter work done, which is nothing but 60 joules. So work done is 60 joules. So you'll have some problems like this. This is a very basic problem. So in these problems, you will definitely draw a free body diagram if it demands. Choose a coordinate system. Is the work being done in y direction or is the work being done in x direction? You'll definitely keep that in mind. Then after you're doing the drawing your free body diagram, laying out the equations nicely, you'll apply the Newton's second law. Up to first 3 steps will be same as chapter 4, where you were doing Newton's laws there. From 4 to 5 onwards is where we will apply the work done is equivalent to force times distance. And then we can also find net work done. There are 2 ways to do this. Either we find the net work done on different forces, or else we find the net force first and then find the work done. This will be more clear when I do solve more problems. So here we go. Let's do our very first problem for this chapter. I know there is problem number 1 on the handout as well, but that's a fairly simple problem resembling the example that I gave behind. Let's work on number 3. How much work did the movers do horizontally, pushing a 46 kg crate 10.3 meters across a rough floor without acceleration? So words are really important in these problem solving questions, and the coefficient of friction is given as 0.50. So the box is moving, so understandably this is mu k, it is coefficient of kinetic friction. How do we solve this? Step number 1 is let's draw a sketch for the scenario. So the sketch says I have a movers were in and they displaced the box through a certain distance. Force applied or force of push or pull, you can write whatever you want, FP or FA, anything is possible, as long as you're not writing FN or FG over here, or you're not writing force of friction over here. Pull or applied force are okay symbols to use. And then they are moving it, and then they moved it to a certain 10.3 meter distance. So we'll put this as 10.3 meters. Force of the push is not given. Do we really need it? Let's see that. Mass is given as 46.0 kgs, and your D is already given. Your mu k is given as 0.50. So you know that mu k does not have units. So what am I going to do first is I'll draw a free body diagram of the scenario. Second, after understanding the problem, I have to find out the work done. So that means I need distance, I need force, but I don't have force right now. So let me find out force from whatever information is given here. The box represented by a dot, normal force represented by this thing, Fn, and Fg represents the force due to the gravity, the force of pull. Since there's mu k, that means there must be force of friction. Force of friction, F of F or Fk, whichever symbol you want to write. Since there is friction and there is no acceleration, if there is no acceleration, that means then it's moving at constant pace. So the net forces in x direction must be equivalent to mass times acceleration. But since acceleration is 0, right, I can write this as Fp, which is in the positive direction, minus F of F, which is in the negative direction, equivalent to 0. That means Fp is equivalent to F of F, that is force of friction, right? So we know that we learned about force of friction before, and we know that force of friction is equivalent to mu k times normal force, right? And normal force, if you look at this diagram here, normal force is equivalent to force due to gravity because it's not moving in y direction, it's lying flat on the ground. So normal force is equivalent to Fg. The y direction forces are balanced since there is no acceleration in this direction, which is equivalent to mg. So substitute for Fn as mg, I get the force applied or force push equivalent to mu k times m of g. Now that I know what I have to substitute for the force of push, I can go ahead and find out the work done. So from the definition of work done, that is equivalent to force. For us, this is the force of push and the displacement that it moved through and the cosine of angle between the two. The two means force and displacement. So since it's moving in a straight direction, theta must be equivalent to 0 degrees. And I can find out the work now by simply substituting mu k mg in here multiplied by d and cosine of 0 degrees. That is mu k mg and d. So why don't you go ahead and substitute values for mu k, mg, and d and try to find out what work done, or what is the work done by pushing the cart by the movers equivalent to. On substituting the values, you should get the value as 2300 joules. You can also put it in the scientific notation, 2.3 into 10 raised by 3. That is fine as well, but mark the unit as joules now. We are into new set of units. So that completes this problem. I hope you understood this. Let us do a similar, based on the similar concept. There will be other problems like 4, and there's one more problem in between on the handout that I have put in the folder, online folder of this week. Those I will not be doing all the problems here with the lecture, but you will get the solutions for them. So now I have picked problem number 9 from the textbook. The mass of a box is given and is accelerated from rest. When we say rest, you must understand it's accelerated from rest means the initial velocity must be 0 by a force across the floor at a rate of 2.0 meters per second square. That means when a box was pushed, it gained an acceleration of 2 meters per second square for a time t of 7 seconds. Find the net work done on the box. You have to find the net work done. So we are not going to leave Newton alone. We still need Newton's second law. So since the acceleration of the box is constant, right, and we can use kinematic equations. So we can try and find out, this is a constant equation formula. So just revising what all is given. Mass is given as 4.0 kgs. V naught is 0. And what else is given? Acceleration is given as 2.0 meters per second squared. Time is given as 7.0 seconds. I have to find out the net work done. But I know what net work done will be net force, distance, and cosine of theta. So in order to find that theta, in order to find the net force, I have to go and seek help from the free body diagram and go and seek help from second law of motion, or maybe second law of Newton's second law. And how do I find d, which is the displacement, given all these values? The final velocity is not given, so I cannot use all the kinematic equations. So I just start looking at the kinematic equations that have displacement in it. The first equation is V is equal to V naught plus AT. I don't need that. because there's no displacement given in there. Then the second one is v square is equal to v naught square plus 2a x minus x naught. I cannot use this one either because I don't know the value of v's. So then the third one, which is x is equal to x naught plus v naught of t plus 1 by 2 at square, seems to have everything to get the displacement. Displacement is x minus x naught is equal to v naught t plus 1 by 2 at square. If I name this as displacement d, that's the same thing as saying x minus x naught. It really doesn't matter. It is the displacement. Plus 1 by 2 at squared. My initial velocity is 0. It's gone. That means my displacement is 1 by 2 at square. I can find the displacement from here. Substitute the values of a and t in here to get the displacement, which comes out to be equivalent to 49 meters once you plug in a as 2 and time as 7. All right. Now I have the displacement. Now my job is to find out the net force. So how do I find the net force? A box of mass 4 kg is accelerated from rest by a force across the floor at the rate of 2 meters per second square. There's no mention of force of friction in this problem. So I will assume that force of friction is 0. The force of friction does not exist. It's moving at constant pace. I can use the net force. Maybe first draw the diagram. The box Fn, Fg, they should be equal, and Fp, no mention of force of friction. So I can write down the net force is equal to mass times acceleration, and the net force only has Fp in it, which is m into a, right? So I can simply write Fp in the formula for work done is equivalent to force applied or push, d the distance, cosine the angle between the displacement and the force. Since it's moving straight, not at an angle, if he had given us the angle, then he would have let us know that the force is applied at an angle. So we have 0, theta is 0 degrees. We can simply write Fp multiplied by d as the net work done, because this is the net force as well. So Fp becomes equivalent to mass times acceleration, and then you have m into a into d. Yeah, it looks like mad, but ma is from here and d is from this equation. You substitute the values of m, which is 4 kg, a as 2, and d displacement as 49. You'll end up getting the net work equivalent to 390 joules. So work on this, substituting these numbers, and spend some time on this problem. Next comes kinetic energy. So you see I have come to 6.3 section. 6.2 is deleted. It's for the variable force. What is a variable force is just giving you an idea. A variable force is simply a force which is applied not constantly. So if you are climbing, if you have to take a box on a hilltop, the force applied will not be constant. So you have to apply variable because the path is varying. So you have seen a problem where you just have a horizontal surface and you're dragging the box from one end to another end. So the force can be applied at constant pace, but not in this scenario. So in higher calculus and integration problems, we know how to do this quickly and easily, but I'm not asking you to do the variable force problems. All right, energy was traditionally defined as the ability to do work, which I also mentioned previously in the beginning slides. So then what is the relationship between kinetic energy and work? Is it the same thing? What happens to the work done on a system? If I do work on a certain system, will its energy change, or will the energy be transferred into the system? So, but what is the form? Does it remain in the state of rest, or does it move? So if I give some push to a box, it will move, or maybe it will not move. So kinetic energy is basically energy due to the motion of an object, due to motion. If there's motion, there is kinetic energy. And we can symbolically write it as Ke. We generally write it as Ke. And the formula for kinetic energy is 1/2 mass times velocity square. You don't have to derive this formula. This is something that you can just keep. You have the formula sheet. And if I say that Ke, the initial kinetic energy, if my object was at rest, or if it was initially moving, so I can simply say kinetic energy is 1/2 mv naught square, because we normally use v naught square as v naught as the initial velocity. And if I have to mention Ke final, then Ke final can be written as 1/2 mv square, because we normally write v as the final. So the change in kinetic energy, change is always final minus initial. So 1/2 mv square minus 1/2 mv naught square is called the change in kinetic energy. We always use change in kinetic energy formula to describe the motion. Now you must be wondering, what will be the SI units of kinetic energy? If this is kg, this is meter square per second square. Do not worry about the units. Kinetic energy is measured in joules, and so is work done measured in joules. So both of them are interrelated. Work is done when there is some energy in it, so energy units will always stay as joules. So there are various types of forms of energy that we know. One is kinetic energy, one is potential energy. We'll come across this in this chapter, potential energy. Then potential energy will be of two types. There will be gravitational potential energy due to the gravity, and then there is potential energy called elastic potential energy, which is the energy stored in the springs or any objects which exhibit elasticity. So there are many toys which have springs in them, and then you press or compress, it jumps up. Something like Chuck E. Cheese has those popping. You put a hammer and something pops out, and then you hammer it down, it goes down, and then it pops up. So that's all potential energy, elastic potential energy getting converted into motion. So that you'll learn about a lot of change in kinetic energy here. So there's a very important formula that is given with the interchange of change in kinetic energy, has been related to net work done. So change in kinetic energy is also called net work done. So you'll have to remember that. And we'll work on several problems based on the change in kinetic energy. It's also called work energy principle. By the way, this formula is work energy principle. And it's a good time now to work on a problem but before I work on the problem, I want to show you how we got this equation. So I'm trying to get a blank slide here. Doesn't show me. No, it doesn't have that option. Okay, so I'll show in this corner. How did we arrive at this formula? We know that work net is equivalent to force net net force, distance, and cosine of theta, because when we talk about network we have to also think about net force. All right. The net force in this kind of scenario, if we look at this car moving from initial velocity to a final velocity, I'll use v naught instead of v1, and I'll use v for the final. We'll keep the same terms. So net work according to Newton's law is mass times acceleration, and d into cosine of theta. That is net work done. So I just want to show you how we can represent acceleration from one of the kinematic equations. We know that v square is equivalent to v naught square plus 2a x minus x naught. So behind we did a problem where I said let's represent x minus x naught for this chapter as d, because it's displacement, 2a times d. So d represents displacement. Is it okay if I subtract both sides by v naught square? Basically I want to isolate a. Minus v naught square is equivalent to 2 a and d. So I subtracted both sides by minus v naught, so the v naught on this side got cancelled. Then divide both sides by 2d. So I get in the next step minus v square. So v square minus v naught squared is equivalent to a whole divided by 2d. Just ignore this line because it's, I don't know why it's this pen sometimes behaves funny. So I have been able to use one of the kinematic equations to represent a. Now I'm going to substitute this a over from here into this part over here. So W of net will be equivalent to mass times v squared minus v naught squared over 2 of d. That's the whole a that I derived from there, into d. And maybe I should write cosine of 0 degrees because the angle between force and displacement is 0 degrees. So that will be equivalent to mass times v square minus this d, and this d gets away, mv squared 1 by 2 or divided by 2, that's the same thing. All right. So if I rearrange the terms, then w comes out to be equivalent to net work done. If I look at this, 1 by 2 mv squared minus mv naught square. So I can separate these quantities by putting the 1 by 2 inside, let it be taken in, and this is nothing but the formula that we have been given up. So this is the same thing that was given to us above here as 6.2. So we can derive it from by substituting for a. You don't have to derive it, but I just wanted to show you how we got this equation. Sometimes the derivations are easy and I will be able to show it, but if it's complex, I myself refrain from solving it for you. So basically you will simply be applying this formula, not deriving it. So you can also write it as 1 by 2 mv squared if we keep the notation the same as v for final and v naught for initial. So you be free to use this form. If the net work is positive, the kinetic energy must be increasing, and the net work is negative, then kinetic energy must be decreasing. If an object is at rest and then you are moving it, the kinetic energy will be positive because you increase the speed of the object. If the object was already in motion and you are bringing it to rest by applying force, then the work done is negative because you are reducing the speed. So this is just a common sense question. So because work and kinetic energy can be equated, they must have the same units. Kinetic energy is also measured in joules. That's what I already worked on. It's good time to now look at one of the problem based on the principle that we learned behind, which is called work energy principle. So how much work is required to stop an electron which is moving with the speed of 1.10 into 10 to the power of 6 meters per second? So we have an electron. Okay, electrons are tiny, and it is moving with a speed of, so that means its initial speed is given 1.10 into 10 to the power of 6 meters per second is given, and your objective is to apply a force and stop it. So that means your final velocity must be 0. That is our objective. And mass of the electron is always constant. It's a known fact. It is 10 raised per minus 31 kgs. So I have to find out what is the net work done. So behind we learned that net work done in terms of change in kinetic energy. The change in kinetic energy will be negative here because we are slowing down something. So hence the electron will see a reduced velocity. So it will be change in final minus 1 by 2 mv naught squared. Okay. So substitute, you can rearrange the terms here. You don't have to, because this one will go away. This is 0 because final velocity is 0. So this becomes minus 1 by 2 mv naught square. You get a negative work because the speed was reduced, so work done is negative. Minus 1 by 2, substitute the mass, 9.11 into 10 to the power of minus 31 kgs, and multiplied by the initial speed, 1.10 into 10 raised power 6 meters per second whole squared, right? And when you solve this using your calculators, go ahead and take some time to solve this. You should get minus 5.51 into 10 to the power of minus 19 joules. That's the amount of work done in stopping an electron that's moving at nearly 1,000,000 meters per second speed. So that's not a lot of energy though. All right, so the work done is negative because the electron is slowing down. We can also work on one of this problem. This is also textbook problem number 20. The baseball of mass 145 grams is traveling 32 meters per second and moves the fielder's glove backwards. So this is a ball that's coming, and this is the gloves. So when it's coming to strike the glove, it pushes the glove back after contact. Okay, and it moves the glove back by a 25 centimeter distance. So that's the displacement. The ball after contacting, so once the ball reaches here, after it contacts, it gets displaced by 25 centimeters too. So the displacement of the ball is also 25 centimeters. The glove moves backwards, that is also 25 centimeters. So our displacement is 25 centimeters. Remember to convert these units. What was the average force exerted by the ball on the glove? So we have to find the forces. So in order to find out what is the average force, I need to know certain things like what is the work done, because I know that net work done is equivalent to net force into displacement and cosine of theta. If you look at the force was applied in this direction, displacement was also in the same direction, so theta is also equivalent to 0 degrees. I just just now I learned that I can also find the net work done in a different way. That is by using kinetic energy relationship, which is called work energy theorem, 1 by 2 mv naught squared, right? So I have the v, I know v naught square, I know v square. So what is the final speed of this? Because the ball is caught, so there is a hint that final speed is also 0. I have been given initial speed. Remember that mass is 145 grams. You will convert it into kilograms and not leave it like that. So it will be 0.145 kgs, and distance will be 0.25 meters when you convert it. Green is my favorite color. All right, and so let's substitute. This one is gone already. I'm getting negative work. I expected that. That's the work. We should write down this as in terms of work done on the ball. Work done on the ball is equivalent to, therefore, minus 1 by 2 mv naught squared. So that comes out to be minus of, if you substitute all the values, minus of 74.24 joules. Do not do the sig fig yet, because we have to apply it somewhere else as well. Then what is the work done on the gloves? The work done by the ball is in an equal and opposite direction. So work done on the glove is going to be same in magnitude but opposite in direction. Minus times work done on ball. That is minus times minus 74.24 joules gives me work done as plus 74.24 joules on the gloves. It's just a conceptual thinking about it. So I got this one. Okay, so therefore I can equate, instead of writing W of work on ball, I can write work done on, I can use this formula 74 plus 74 point, therefore 74.24 joules must be equivalent to force, that's net force on the glove, force on glove multiplied by the displacement that it moved, 0.25 meters, and you already know cosine theta is 0, so that gives the force on glove exerted by the ball on the glove, that is what we are finding, on glove, is equivalent to, divide 74.24 joules divided by 0.25 meters will be equivalent to 3.0 into 10 to the power of 2 newtons. See, we are finding force. Don't get caught up in the units. We are finding force, so hence the unit will be Newton. And it is in the direction of the original velocity of the ball, so that's why it's plus. It has a plus sign because the glove faces the force in the same direction as it was being pushed. So that is one way of understanding this. Next is 6.43 section, which is potential energy. Kinetic energy was 6.3. So what is potential energy? So potential energy is basically energy possessed by body by virtue of its position. By surroundings, I mean position. So if a rock is on the cliff and somebody pushes it, or it naturally rolls down and somebody is standing down here, what will happen? This rock has the ability to do work, and it can kill or damage things. So the rock has potential energy in it, which is getting converted to kinetic energy. So there is a conversion of energy from potential to kinetic energy, and then the result is some kind of damage or some kind of breakage. So familiar examples of potential energy is a wound up spring, a stretched elastic band, and an object at some height. So if you have a spring that is wound up and you release it, what is going to happen? If there's a toy in front of it and you are compressing it, it will go ahead and knock out a ball in front of it. So there are scores of toys like this. And if there's a stretched elastic band and you release your hand, it was held up like this, then it will compress back or do some work. So this is an example of elastic potential energy, not gravitational potential energy. This is elastic PE, but this is an example of potential energy due to gravity. Due to gravity, also called gravitational potential energy. All these forms of energies are mechanical energies: kinetic energy, potential energy, which is two types. One is elastic and one is gravitational, are both form a part of mechanical energy. Since physics 1 is all about mechanics, we are not going to work on nuclear energy, chemical energy, solar energy, or any other forms of energy. We are simply focusing on mechanical energy. So the gravitational potential energy, if I have a brick which was lying down on the floor and we are lifting it up, so the external force is the force exerted by hand, and then the gravity also is exerting force in the opposite direction. And if I lift it with in a constant fashion, like I'm not accelerating it, then the net forces will be balanced. The external force will be balanced by force of gravity. And if I raise this at a constant speed, or I'm moving it uniformly, not accelerating it, not throwing it up, then the force is given by mg. This external force balances Fg, which is mg. So that's why we're writing mg here. And d is replaced by the height, which is just the formula for work done. And gravitational potential energy is always given by weight multiplied by the displacement. So h is the height. Height is like final minus initial. You raised it from ground level to the height, so you get y2 minus y1. Work done is positive. But similarly, if you're bringing the brick down from a high potential to a low potential, you may be able to see a negative sign also. So the basic formula for gravitational potential energy is simply mgy or mgh. This potential energy can become kinetic energy if object is dropped, the same example that I was talking about. And the potential energy is a property of a system as a whole, not just of the object, because it depends on external forces. So it's not an intrinsic thing. It depends on the gravity as well. It turns out not to matter where from you start measuring. If you are measuring from the bottom to the up, the formula doesn't change. On the contrary, if you're measuring from up and down, the formula doesn't change. Gravitational potential energy is also dependent on change in potential energy, which is m, g, and h, where h is basically nothing. It's final position minus initial position. That's the height. So I'll give you this assignment to work on problem number 29, which is based on gravitational potential energy. We will list out all the quantities here. A hiker who's 66.5 kg starts at an elevation of 1270 meters and climbs to the top of the peak. What is the hiker's change in potential energy? What is the minimum work required of the hiker? And can the actual work done be greater than this? So we know that work done is equivalent to m. Work done in going up an elevation is gravitational potential energy. So this work done will be mg in h, which can also be written as mg y minus y naught. You can go ahead and find out. So your y naught, the initial position is 1270 meters. Your final position is 2660 meters. The mass of the hiker is given as 66.5 kgs. You can go ahead and find the gravitational potential energy, which is also work done, but it's good to write it as PE of G, mg of y minus y naught. So m is given, g is given. Go ahead and solve this and think about these questions. Next time I'm going to put the solution for this along with the PowerPoint version of the audio video file that I put always next to the video file. All right. Please go ahead and study section 6.1, 6.3 and 6.4 completely, because you'll need this content to do the lab on energy. Do not start your lab without looking into this part, because we are going to discuss in that lab. If you don't know what is potential energy, if you don't know what is kinetic energy, you cannot do that lab. So, and knowing the formulas for Ke and knowing the formulas of Pe will be extremely important, because you will be learning about conversion of Ke to Pe and Pe to Ke. So that's what the lab is about. Thank you, and see you in office hours on Tuesday. And I'm hoping to discuss your exam too, and you'll get the grades online though. But if you have any questions, you can contact me, and we can discuss. Also, we can discuss anything related to this chapter during the office hours. So I would really suggest that you use your office hours. You should be ideally free around that time. That's the class time. Okay, so see you and have a good weekend.